Hello friends, welcome to my back to my YouTube channel, High Performance Computing. In this channel, I will teach you about the numerical methods in C++ programming. For starting, this is the starting lectures of my channel. So I am teaching first starting finite element with C++. So, in previous lecture, I have told you I have divided finite element method with C++ in two parts. First, the theory background of the finite element method, and second part, I will teach you the programming, how to implement these things. So, this is the third lecture of my programming. So, in lecture 2, I have told you about the what are the partial differential equation is involved and boundary conditions. And today's lecture, I will teach you about the strong form and weak form. Let's go. Strong form and weak form. So today's content is strong form, weak form, why we do weak formulation, and example. So what is strong form? Strong form is nothing but original or unaltered differential equation of the physics problem. And it consists of the boundary conditions. Like in previous lecture, for the one-dimensional del by del x, a del by del x, sorry, del y by del x plus bx equals to 0. This is the one-dimensional governing differential equations for the different physics problem. You can check I button here, or you can go to the description box and description. You will see the what is the y for the different variables for the different what is the different dependent variable y for the different physics problem and a for the different physics problem and b also. Now it consists boundary conditions. So in previous lecture, I have told you about that there are types of boundary condition. One is Dirichlet boundary condition. Second one is a Newman boundary condition. And third one is a Robin boundary condition. Please go to the previous lecture. You will see the what are the these kind of boundary conditions. Now, weak form. It is nothing but a weighted integral of the strong form. And after the integration, you will naturally implement the boundary conditions inside the weighted integral form, and it uh, decrease the continuity requirement of the dependent variables in approximate function of the independent variable. So why we do the weak formulation? As I told you previously slide, it weakens the approximate function's continuity requirement for the dependent variable. It gives flexibility to choose easy approximate function like in strong form del by del x a del y by del x. It looks like u, so let me change it y. Okay, plus bx equals to 0. So here order is 2. So we required second order approximate function y is equal to second order approximate function of x. Mostly we will choose polynomial function and approximate as the approximate function. I will teach you in next lecture about the polynomial functions. And so today's now come to the example part. So strong function, colored it in red. Strong form. Okay. It's very dark. Let me reduce it. Del y del x a del y by del x plus bx equals to 0. Let's two boundary condition will give y 0 is equal to 0, a del y by del x at x equal to L is equal to some q. Okay, now come to the weak form. As I told you, it is a nothing but weighted integral of strong form is called weak form relation. So del y by del x plus bx to 0. So let's break it. Now apply. We know that. Let's take it as a. We know that differentiation of two function and multiplication of two function is like will be differentiation of first function and second function as it is plus first function as it is differentiation of second function. Okay, now transfer this the first term of the RHS into LHS, so it will become del by del x omega a del y by del x minus del omega del x a del y by del x equals to omega del y del x a del y by del x. Now integrate both sides with respect to x. Okay, let me change it to the red color. It will be very good. So dx integrate dx. So let me give you this equation 1 and equation 2. From equation 1, we put the equation 2 into equation 1. This term in RHS and this term in LHS are equal. So we can put this here. So how it will become? Let me change. Del by del omega a del y by del x minus del omega del x a del y by del x dx equals to, sorry, not equals to, plus integration of omega bx dx equals to 0. How much? Let's say there is a length boundary condition I have told you. Q x equal to 0 and x equal to L. So integrate 0 to L, 0 to L, 0 to L. The integration of these two variables will become omega E del y by del x minus del omega 0 to L del omega del x A del y del x dx plus omega dx equals to 0. Here 0 to L limit also. Can we transfer this into this side? So we can write here as like this del y del omega y del x A dy del y by del x dx plus, oh sorry, not plus, equals to A by del x 0 to L omega bx dx. So as I told you in previous problem, no, not previous problem, sorry, in previous slide previously I told you why do we weak function. So initially the derivative order of the differential equation was second order here also, but the order of requirement of y approximate function has been decreased. Here only one first order is required. Now this second order is changed into transferred to the limited parameter function omega, and I told you boundary condition implemented inside after the integration. So this implement the boundary conditions, if you can see. So this is the weak form of the your bond governing equation. Now next lecture I will tell you what is the approximate function, how to choose the approximate function. Okay, thank you. Please support me, subscribe by subscribing this, and like and share. Thank you.